Testing, testing, testing. How are we doing? Howdy, who do we got on the line?
It's David.
Hey, David. So I take it
Hey.
you can hear me okay.
I can. I'm trying to get my my phone to, my earphones to pick up the line because actually I'm trying to put my daughter to sleep right now.
Ah, okay, gotcha. Okay, so that invite URL actually worked this time, so I'm happy to see that.
This does not seem to be working. Okay. I can make this work. Maybe. Back. Okay. Okay, can you guys hear me?
I can hear you.
Okay, great.
Okay, Michael, welcome.
Yep. Pardon me?
Welcome.
Oh, thank you.
We should have one more person joining up, I think.
Yeah, that's cool.
Okay, Michael Claggett was the other RSVP. Do we want to give him a couple of minutes to join up before we get going here? Or do you want to... Okay. I'm just going to try a screen share here to make sure all the technical stuff is working. Okay, can you see my screen here?
Yes.
Yeah.
Okay, great. Okay, and is that font size a bit small there? Make it a little larger?
That would be helpful.
Okay, just a second here. Okay, how's that looking?
Yeah, it looks great, actually, to me.
Okay, cool.
Okay.
Hello, Jonathan.
Hi, Paul.
Welcome. Have you joined up to any of these before? I'm trying to remember.
No, this is the first time that I've actually participated in a Google Hangout session.
Okay, awesome. Well, glad you could make it.
Well, thank you. Thank you for doing this.
Sure. We're waiting for one more person, maybe. I guess we'll give them a couple more minutes to join up, and then we'll just kind of kick off the discussion here. So we're just kind of hanging out silently at the moment.
Sounds good. In the meantime, I'm going to look for some headphones. See if I
Okay, cool.
can get them plugged in.
So, Jonathan, what's your background? Have you doing much functional programming? Are you just interested?
Primarily interested. I certainly would like to do some functional programming on the job, but I don't see that happening anytime soon. So at this stage, it's primarily an interest, and yeah, I'm not the only one who has that interest at work too. But
Okay, great.
yeah, it's primarily a Java and JavaScript environment. I guess it could be argued that JavaScript is somewhat functional, but
And you're getting a few more hints that direction with Java 8 as well.
oh yeah, exactly, yeah. I took the functional programming principles course on Coursera. It was in Scala,
Okay.
and that was a lot of fun. And the course actually, I would say about 30% of the course followed this structure interpretation and computing programming course. It actually, a lot of the, like for example, the Pascal's triangle, that was one of the exercises, that were taken from the book. Yeah, and that was a key reference as well. Yeah.
Okay, cool.
Yeah.
So have you done any of the reading, or are you just coming to this kind of cold?
I did the reading, and it was a couple weeks ago, and unfortunately I didn't get to the exercises, which I'm
that's okay, no worries.
not too thrilled about, but oh well.
Difficult to make the time a lot of times.
Yeah. It's
Okay, so looks like we've got all of our RSVPs here. Okay, Michael Claggett.
Yeah, hi.
Hi. Do you prefer Michael, Mike?
Whatever people comes to people, doesn't matter.
Okay.
I answer to both.
Because we we have two Michaels on the call, so we'll have to distinguish between you two somehow.
Okay, you can call me Mike.
Okay.
I was here forever.
Yeah. Okay, what are you staking a claim to then?
Michael.
Michael, okay, so fair enough.
So I'm Mike and you're Michael. Great.
Okay, great. Alrighty, so everybody else, how are you feeling about this chapter? Get a chance to do the reading, any of the exercises?
I did most of the reading and most of the exercises, but I didn't get through all the exercises.
Okay, awesome.
And I got through the reading, but not too many of the exercises. And the reading I did maybe, I don't know, a month ago, something like that.
Yeah, we were a little late getting this one onto the schedule here, so we'll be doing the next one in about 2 weeks here to catch up to the in-person session. So, and Michael?
I'm pretty far behind, actually.
Okay, that's cool. So, no, I mean, that's what we're here. It's I think the most important thing for a project like this is not to sort of let the pressure of the fact that you kind of procrastinated a bit keep you from just pushing on through. So, I mean, my opinion is that the more of the book that you just sort of at least expose your mind through and the discussions, then if you go back in the future, it'll be that much more meaningful. I mean, you can extract a lot from it without doing the exercises. The more exercises you do, I would definitely say you get benefits from them. There's sort of an additive effect where they're sort of leading you through some painful things along the way. So you reach the moment of enlightenment where you say, okay, that's why we need this particular type of abstraction. So how do we want to do this here? Do we want to go over sort of some of the key points in the chapter first, or just dive right into the exercises?
I think talking about the chapter would be beneficial because I read it. I actually read it like a month ago or something.
Okay, yeah.
So I'm not 100% sure where. I mean, I remember that it was talking mostly about creating cons and creating a lot of the functions that we were already using from scratch, using cons and car. But other than that, I don't quite remember too much.
Okay, just one second. I'm pulling up my notes here on my.
Is this the part of the chapter that talked about trees and how to develop more hierarchical data structures from the basic primitive?
Yes, that's exactly so. And then the second half of the chapter then moves on from the hierarchical data structures to sequences as interfaces to various things, and then the extended picture language example.
Right. But that's the part that we have that we're going to cover next time, right?
That's the part we'll cover next time, yeah. So this time it's primarily sort of getting familiar with pairs and conses and lists, and then also sort of constructing various data types ourselves out of these primitives, and then operations to work on these abstractions.
Paul, did you? What's the in terms of the exercise numbers? What are we covering from?
What we are covering is let me actually. I'll flip over to my screen share here. Entire screen share. Okay, so here's what we've got. So this is exercises 2.33 to. No, this is the wrong one. Excuse me here. We want 2.2a. There we go. .17 through 2.32.
Oh, okay. So I might actually have done all the exercises then.
Okay, you can see there's 3 that I did not get a chance to finish up. I was running a little behind myself, so I actually did most of those in a couple of days before the meetup for the in-person session for 221 and 222. and I still haven't
Okay.
done 223 yet. So I'm rushing just like everybody else here to stay in one place.
Oh, okay. I actually did do all the problems for this one then.
Awesome.
Though not to say that I did a great job, but I did do them.
That's okay. I mean, that's good for the discussion. Okay, so I guess the let's see. First of all, let me just get this compiled here. Okay. So really, so section 2.1 starts off with this really old school discussion of how you build up a list from its component parts, and so this goes all the way back to the original implementation. What do we have here? Oh, sorry, wrong language here. Okay, and you have just seen one little trick there, and that is that unlike the text, the version of scheme that I'm using here, Racket, uses null instead of nil. So nil was a pretty early version. They're the same concept, basically. And
Paul,
yes.
Can I ask a quick question?
Sure.
This is Mike. What environment are you using? Because I don't know that I have set up a good one.
Okay, so what I would recommend if you're trying to set up an environment for doing this is just using Dr. Racket. So Dr. Racket has really good support for doing these exercises. I've hopefully launched it here. I personally am using Emacs. I'm using Emacs using Racket, which is what Dr. Racket uses as the back end. Racket is a modern scheme, so it isn't exactly scheme anymore. It's sort of done a lot of extensions.
Mm-hmm.
And if you do that loads all of the SICP compatibility libraries for Racket. So if you don't have any particularly strong attachment to an environment, or a particular, you're driving yourself to learn a new environment, Dr. Racket's pretty straightforward for a lot of these things. And it's got some nice features.
Okay.
I mean, so it has these nifty little graphical things that can show you where things were defined. Stuff like that. And it's got very good debugging facilities for stepping through. I personally am using Emacs because I really like this environment called org-babel, which was horrifically painful to get set up originally, but I'm heavily invested in Emacs. And the nice thing about about Emacs with this is if I write up my solutions to the problem like this with some commentary, then I can stick the scheme in a code block. And if I use this little session tag here, then it's all run in sort of a continuous scheme session in the background. So all the code loads into the same one. And then if I hit Control-C to evaluate it here, it sticks the result right in the text. So it's a good way to sort of build up sort of a story about the code you're writing. So a lot of people use this for what they call literate programming type activities. And then if you do a, let's see, org-babel tangle. I guess I don't have this one set up properly for that, but okay, so like here's an example. These are my all the code for my other session, or for 223 and 224, which is where I just got this working, where it actually goes through and pulls out all the code blocks and sticks them in a single program file. So that's another way to approach doing that. Okay, and it also gives you editing of, you can pop into, actually edit it in scheme mode, so you have all your nice syntax highlighting features and your parenthesis balancing stuff. And so now if we do, and so on. So it's a nice sort of all-in-one environment, but it's definitely not as user-friendly as something like Dr. Racket. So with Dr. Racket, you can really just start typing the scheme code, and then you click Run, and it does all your answers at the bottom like that there. Okay, so this actually here is a something that kind of I found confusing when tackling Racket first. So Racket, so is everybody here familiar with immutability?
Sure.
Yeah.
Yeah. Okay. So Racket has made the jump to immutability, which is not really part of the scheme standard. And so they distinguish mutable pairs, in this case with M cons. So this is a mutable cons cell here. And that means it does not print things as nicely. And so you end up having to sort of tweak things to get your traditional Lisp printout if you're working in Dr. Racket. You can do it, but these two sections in particular, you get a display which is slightly different, even though you can still do all of the exercises.
What does mutability have to do with printability?
Okay, so in a okay, so actually this is a good place to discuss this here. Okay, so if we do, okay, so the main point of section 221 is you know, what a list is. And so a list is really a convention. So your cons cell is a pair. It's a data structure that's sort of got a front and a back, or a left and a right, however you want to look at it. So you can put something in the first part of it and something in the second part of it. And that makes a cons cell with one on the left and two on the right. So it gets printed out here with what's called dotted pair notation. However, if you're building up a list here, there's this conventional structure that they have.
It's Mike again. Is there anything you can do to help me out? I'm losing the first, maybe it looks like probably 5 characters of your screen.
Oh, okay. Yes, there is. Hold on 1 second here. And those would be important characters, given the way we're going here. So
I'm guessing. Oh, perfect.
How's that?
Yeah, that's perfect.
Okay. I just made a tiny window and put it on the left.
Oh, you know what? It went back to, now I'm losing like 1. But that's all. I can probably figure it out.
How's that?
Perfect.
Okay. It actually is important to see that left character, because even though we have not discussed quoting yet in the context of the book, that is what we're getting here. So, so we do 1, 2, 3, list 1, 2, 3 like that there. This is actually sort of what we actually have behind the scenes here is if this is a cons, we've got 1, then on the right, 1 on the left, on the right we've got a 2, and then a 3, and then we've got this nil or null in the final position. And as long as something is in that form, it's the scheme interpreter is going to print it using this nice list notation. So in this case, that little quote mark at the beginning and then 1, 2, 3. And if we start violating those expectations, so let's say we do cons 1, cons 2, and for the last one here we do 3, 4. Okay, so it starts printing it as a regular list, and then it says, okay, we've hit something here that violates what I expect the list to be, so I'm going to start printing it as a dotted, using the dotted notation. So when we take this into the context of Dr. Racket here,
Any chance you can modify this as well, or is that harder?
oh yeah, no, that's easy. How's that?
Perfect.
Okay.
Did you need to change your line back?
I changed my line back. Which line is that?
Did you need to change your lang back, or else change that to nil?
I just changed it to nil here.
Yeah, okay.
Okay, so, and for some reason, I'm having a little bit of trouble. So in the Emacs here, I have some code which is supposed to put this into full compatibility mode, this line right here. And for some reason, it is not fixing everything. It's fixing some of the stuff, but one of the things it does not happen to be fixing is the nil versus null thing, and I just haven't had a chance to dig through it. So you can see here that this is a directive that gets stuck into when it's turned into a file, and this is sort of the equivalent that has worked in previous times for in the context inside of Emacs. So these are kind of equivalent directives here. Okay, so the difference here in terms of printing is that Racket, in this case here, in this case the Dr. Racket interface is detecting, okay, these are not what I am now thinking of as my conventional cons cell. These are mutable conses. So instead of giving you the spiffy list notation, I am just going to print out each of these as a mutable cons. And there is a way to change it, but since I'm not using Dr. Racket, I haven't dug into it that deeply. And my guess is that Neil Van Dyke, who makes the Planet language package, probably needs to make an update to the language directives to make that a little friendlier to use. Okay, we good?
Yeah.
Okay, cool. Right, so... Yeah, so I mean, is everybody sort of familiar or comfortable, I guess, with the concept of these, how you build up lists like this? And if you've got something sort of in this first cell that's also a list, it's going to render that first part as actually a sublist. And you can build that up more. And of course, all of this can also be done using the convenient list notation as well. Like that. But sort of the key point for section 221 is how you build up these types of sequences. And so if you look at sort of the more modern versions of Lisp, particularly Clojure starts violating a lot of these traditional Lisp expectations. So if you go back to the original versions of Lisp, just about everything really, it does boil down to cons cells underneath. And one of the choices that Rich Hickey made when he was designing Clojure was to say, okay, well, given sort of the modern range of data structures we have, it's going to be convenient to, if not everything is built up using these, what are effectively linked lists. We're going to have sort of a built-in vector type and built-in map types and so on. So, and I guess the last piece, if you're not too familiar with the traditional Lisp notation, is the car and the cutter. So these are sort of remnants of the names of the registers on the original machinery that the original Lisp was actually written to run on. So car is the contents of the address register, and cutter is the destination register. I can't remember exactly. But anyway, but basically, car means give me the left, and cutter means give me the right. And in the context of lists, basically, you can also think of car as being a head function, and cutter as being a tail function. So it basically chops off that first element of the list. And since everything that's left is still in the correct format, since what we have left there is effectively cons2, cons3, null, basically all we've done is sort of taken the contents of the right side of that of the cons.
I'd like to make a quick jump in quickly and say that with because I was playing around with Clojure and these ideas the other day, and what I noticed was that cons still pretty much works the same way as it does in every other scheme, except that you have to take into account that because he has these two types, or at least two types of what I call arrays or lists. He has the vector and the proper list and all these other things. That the main difference is that those are actually reversed lists. So the only it's only when you use conj that it's different. But cons still works pretty much the same way.
Yes, actually, that's a really interesting point. One of the choices that was made in the design of Clojure is that instead of sort of the list itself, the linked list being the fundamental data type, the fundamental abstraction that's being used is something that behaves a lot like a traditional Lisp list,
right,
but can actually have a number of different implementations. And one of the cool things about this is it means that anything that you can treat sequentially, anything that you can say, give me the first of thing, and then give me everything else that's left after taking the first thing, you can do all of these traditional Lisp manipulations on. Which
right.
means that you can use map on your vectors, but you can also use map on your hash maps. And you can use also, of course, then the various infinite data structures you can build up. So using lazy sequences, as they're called. So yeah, that's actually a really good point. There's sort of a tendency to be biased against using a standard list in Clojure. And a lot of that is because of, I believe, things like cache coherency and so on, because a lot of times it can be less efficient to use a list for a lot of a linked list for a lot of operations.
And then but most of this efficiency comes from the fact that it's the way that the list is actually. And I'm saying list, but like for instance in Scheme, if you want a list that's more it's going to be more efficient with like take the last item, or first in, first out. Then you create your list in a certain way. So I think in Clojure they sort of just take care of that for you, and they say, well, think ahead of time what this thing is going to be for. Is this thing going to be like first in, first out, or is it going to be last in, first out? And then in that case, use the appropriate type of list. Whereas in the old scheme, you kind of have to figure out that ahead of time and then create the list, the appropriate way, like using like left fold or right fold or blah blah blah. If that makes sense.
Yeah, absolutely. Yeah, I mean, of course, the big disadvantage for your linked list for most applications is that to retrieve a random element, it's big O of n time, where n is the length of your list. So the only way to get an item out of the middle of your list using sort of the basic data structure, of course you could build up a better one yourself, but if you just have the basic one, you have to start at the head, and then you go step, 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 step until you actually get the item that you're interested in. And of course, picking a particular item out of a sequence of items is an operation that one does an awful lot in modern programs. Now, actually, you also mentioned the use of conj, that's C-O-N-J.
Right.
Doesn't work here. And in Clojure, that is sort of a polymorphic type of operation. And it says, given whatever the underlying type of sequence is, do the right thing to add a new item to it.
Right. And so there's where you really see the difference between scheme and Clojure, I think, as it applies to lists, is the conj and the fact that there are these sort of different types of lists in Clojure. I think that's the main. But you could, like, if you forget about conj and you can actually do everything just using cons. It's just more difficult.
Yes, exactly. And and of course, Clojure does actually implement a big chunk of the data structures in Java for efficiency.
So if I'm understanding what you're saying correctly, it's all a sequence abstraction. Is that correct? No matter what the underlying data type is, if you're using this conj to manipulate it, is that correct?
Yes, so in Clojure, basically it isn't necessarily a sequence data type, but it's something that can be treated as a sequence. So
so it's an abstraction.
Yes, exactly. So it's a slightly different than actually a data type. So one of the interesting things you have in Clojure is the ability to do protocols. And so a protocol you can think of sort of in object-oriented terms as being like an interface.
Sure.
But it's an interface that you can apply to things that you don't even own. So you can say, okay, here's some data type I have in this library. It would be really nice to treat it as a list, so I'm going to do it as, I don't know exactly what the Clojure is, but I'm going to make it a seq, which is the sequence type. And then in there, I'm going to define a way to do first, and a way to do rest. However, I forget exactly what the implementation. But basically, you can say whatever my object is, now suddenly I can do all of the regular sequence things on whatever that is. And so it's sort of moving away from saying, okay, we can build absolutely anything we need to from lists, to saying, okay, we can build anything we want, and then we can treat it the same way using all of these highly general, higher-order tools that we've constructed around these abstractions.
Wow, that's actually pretty interesting because that's exactly what this chapter is dealing with. This chapter, or maybe it's the next chapter, I'm not sure, but it's essentially trying to get you to the point where you start thinking of processes as streams of streams that you'd manipulate. So it's interesting that Clojure took that one step further.
Actually, I found it really interesting, sort of exactly how many of the things that we've been reading in SICP here have actually just sort of been shined up, rethought, and planted into Clojure as if they were new. I mean, he definitely gives credit where it's due, but I was really amused in one of these sections here. I think to read a reference to transducers, which of course are Rich Hickey's big new release. So, and there's sort of an offhand comment in the text that map is like a transducer, and of course the transducer is from engineering where you're changing one kind of energy to another. But it's a very evocative term, and it sort of gets the idea across about the types of operation you're doing. And for Rich Hickey's transducers, once again, it's sort of this higher order thing where instead of saying, okay, I can do all this stuff to a list, it's like, okay, I can say how to do stuff. It's basically the idea. So here is a process for doing things to things. And then you can take this process, or this process instruction, and slap it on anything. So you can slap it on a regular list, and it will chew through it and produce a new list that has been transformed. Or you can slap it onto a channel, which is another relatively new abstraction from Core Async, and it'll chew through all the items in the channel forever. And it doesn't need to know that there's a channel that it's working on.
Yeah, and I think like all of these ideas, like the channel idea, and I guess the transducer idea, then they're all really part of they've all come out essentially as progressions of what SICP talks about all the way back in the 80s, which is essentially dealing with streams of data, manipulating things in little packets. So.
Yeah, absolutely. And in fact, in chapter 4, we get to the point where we implement lazy evaluation, and then we also implement streams. So streams were originally on the docket to be included into Clojure, but they ended up getting scrapped in favor of the channel abstraction, I believe. So, yeah, I think one of the things I'm really enjoying about this trip through the book is exactly how much it sort of is enlightening all this other stuff I've been reading and hearing about Clojure and about other, Lisp-derived languages and about Scala and stuff like that.
Right.
It really is all just incredibly relevant these days. Okay, so any thoughts or questions about sort of these basic cons operations here?
Nope.
Okay, cool. So, is that good?
Yeah, it looks good to me.
Okay, so is there anything else to sort of think about in Chapter 1? So other than that, there's sort of the concept of mapping. Yes, mapping is, of course, highly key. Somebody else want to talk about mapping? Or shall I keep talking? What do you think?
Yes, please.
Yeah, go ahead.
Okay, so I'll talk about mapping a little bit. So one of the really nifty things about the process that the authors of SICP take you through is how you really are, being a blacksmith, building up your own tools from the basic parts. And if you've used a functional language or even any modern language that has taken sort of a few ideas from functional programming, one of those key ideas is mapping. And so that is, you have a sequence of things, and you are going to perform some operation on every element of that sequence and generate a new sequence as a result. So let's see here. Map defined. Okay, so if we map, so instead of sort of writing in the text, they've got the scale list operation where you go through and you say, okay, we're going to walk through this list and we're going to multiply every item by some factor. Okay, well instead we are just going to do a map, and for every element in the list, we're going to multiply it by
2.
By 2, say, yeah. And
Oh, you forgot to close your lambda.
Yeah.
Thank you. That's it. There we go. And so, I mean, sort of that right there is sort of the fundamental insight of higher order functions. It's, we can take some operation, in this case, our multiplying by 2 there, and apply it to every element of a list. And the machinery that makes that happen, the map, does not care what operation is being done. And as we said, in Clojure, it also doesn't care what we have here as long as it knows how to get the first thing and the next thing.
One thing I want to add about map,
yeah,
which I learned this weekend listening to one of the SICP lectures that are on video, is that map, whenever you look at map, it's it's you can think of it as a recursive procedure, clearly. But the interesting thing about the map is that it also hides the fact that that there's a terminator. It doesn't quite hide it, of course, because if you know how map works, then you know that it must include, like any recursive procedure, it has to include a termination point.
Mm-hmm.
But if you see a recursive call, like if that includes a map within it, and then you're wondering where is the actual terminating thing, then that's your answer. It's the fact that the map that was included, that it could be the thing that's terminating everything ultimately.
Right, and in fact that's what we've got right here. So this is just a very simple definition of map here, and it basically it's exactly that recursive procedure you just described. It's going to check, so we've got a list of things here in items. If it's null, in that case, if we recall that null is actually our empty list because we're consing everything onto that. So we're building that up from nothing. That's our our neutral operation. If that's it, we just return nil. But as we go along, we're building up our cons here and applying the procedure to the first thing, and then applying the procedure recursively to the rest of the things. And it just chews through the list and produces a new one. Are there any useful exercises to look at here with that in mind? Let's see here. Okay, so 21 is squaring a list. Okay, that's pretty straightforward. It's not necessarily that useful. So what they do for a lot of these here is sort of give you something that leads you to the necessity for the machinery that's being introduced. So in this case, square list here, this is clearly exactly that form we just saw. So it's saying, okay, well, go through this and find sort of a procedure which is going to go through and square a list. So you can get ready for the idea of doing something to a list. And there were two implementations. What are the two? And this is, of course, showing the equivalence of those two, showing that you can do it yourself, building it up recursively, or you can just define it in terms of map. And of course, if you can think in terms of map, it makes your code that much more terse, because map is handling all of the machinery for you. And okay. Now this one here, exercise 222, is a useful one to look at as well. If you recall the exercises from chapter 1, if you did any of them, one of the things that they harp a lot on is the difference between iteration and recursion, and how you can use them to build the same types of tasks, or the same types of processes behind the themes. Or rather, processes that do the same thing, but they might end up having different performance characteristics. So, in a lot of cases, a recursive procedure is going to sort of build up stack frames as it goes on down. And so it's going to end up taking a lot more space than something which is an iterative procedure, which is one that's able to, even though it's written recursively, since it happens in the tail position, after it's already done all the work it needs, it can just throw away, all of the state and immediately jump back and do the next step. So, how do people feel about that?
You mean the difference between recursive and iterative, like?
Yeah, particularly, if you haven't looked at chapter 1 much. Everybody comfortable with this concept?
Yeah.
Yeah. I think I finally just have gotten comfortable with it enough with recursive procedures that I like them now. You know how I used to be like, oh, I hate these recursive procedures. Well,
yeah,
I've changed my tune. I think they're great. And And I do think that they are actually easier once you get them. They are actually easier to think about.
Yeah, there's an old saying that there's like I can't remember. There's like three things that are sort of the major stumbling blocks for programming in the traditional sense. One of them is pointer arithmetic from C, and another one is recursion, and I can't recall what the third one is. But those are sort of your two of the big jumps that programmers often have to make in order to start to think about code in a different way. But again, that's the value, I think, in doing the exercises, because it's a difference between reading this and sort of running your mind through the process enough that you can say, okay, I can see how to think about a problem in this way. And so this one here is then taking all of this work that was done previously and showing that, okay, well, all of a sudden, what we have is a list that ends up in reverse order. So, David, did you do that one there?
Yeah, which one's that one? That's problem 22? Yeah, I did do that one. Let me see. I think I pretty much did what you have there. I could share my screen. I don't know how to do that. Just
on the left side.
Oops, sorry.
There should be a little green arrow thing.
Oh, yeah. Okay, so go ahead and share. So do I do share entire screen? Is that what I click on?
That's what I've been doing.
Okay. And so can you see my screen now?
I cannot see your screen.
Hold on. I guess I have to click on share.
Ah, there we go. That was looking promising.
Okay. So this is my answer to square list. I think it's pretty much what you have. Am I wrong about that?
Just make yours a
It
little
could
larger.
be. I mean, there are a couple of. Oh yeah, so I defined it one as an iter. Did I not do this as a recursive procedure? I might have not done this as a recursive procedure.
Well, that's kind of the thrust of that particular question.
Okay.
It ends up in reverse, but why?
Okay, so I think that my answer is not very clear. The iterative square list returns a reversed ordered answer. The reason for this is the order, the first values worked on will be the last values of the empty final list. I think I had a hard time with this, but I kind of like worked through it little by little to see what was going on, and I realized what was going on, but
Yeah, that's really, so this is one of these pieces where they're having you sort of get down to the nuts and bolts of the consequences of using this particular linked list data structure. And that is, if you're going to add something to a Lisp-style linked list, the only operation you can do on it in big O of one time, in constant time, is adding something to the beginning of the list. And so,
right.
when you call your cons, each new item is being added to the left side of the list, not to the right side of the list. So if you look at how the conses are set up in a list definition, they are recursive. So there's something on the left, and then there's a recursive cons on the right. And that has something on the left and a recursive cons on the right. Well, in the version of iter that is being used to implement it in this problem here, you can see it's consing the new thing, the first thing it encounters, and then moving on to the next thing. But then the next thing adds it to the left side, so it's building up the list in reverse as it goes.
Yeah, I think I guess I had the wrong answer for that then. Yeah, I see it now.
Yeah, it's kind of tricky. So, and then the second part of the example, where he changes the arguments to cons, So saying, okay, well, to make it backwards, we're just going to build up the. We'll just put the the thing that goes on the. We'll just change the order of our arguments. But the problem is you end up building an ill-formed list.
Right.
So, because if you recall, because you can see what's going on is all of a sudden you aren't building a nice recursive structure. So, at the very first moment, I'm just going to flip back to my screen for a second here.
List of lists, essentially.
Right. So, what we have here is if we're recursing the other way, so we start off, and if we've got 1, 2, 3, and if we square them, and so the first thing we're going to do is if we start squaring, we'll say, okay, so we're going to put everything else there, and then we're going to put the square of the first thing here. And we can see that already what we have is not a valid list, because a list needs to end with a nil or a null. And so then when we put the next thing in here, we end up with cons, everything else, and then 4. And then we go one deeper, and we go cons, everything else, 9. And then this final everything else is replaced by nil or null. And so you can see what we have there, the numbers are reverse, but it isn't actually a list because it hasn't been built up correctly.
So I guess the point of that problem essentially was that recursion is definitely needed in order to maintain. Sorry.
Yeah, that's okay.
In order to, what it is that I have. Yeah, in order to maintain your, list, a proper list.
Exactly. So, so this is one of these places where the way things are implemented under the surface really does matter. And so, since we're building everything up from sort of these very primitive pieces, we have to understand the primitives all the way down to see how it's being built up. But the nice thing is, though, once you're, as you start moving up the ladder of abstraction, if you've written your lower levels right, suddenly you don't have to worry about those lower level things anymore. And so that's all this bits about writing accessors that we get to. I can't remember if is that in 2.2. No, I think that's 2.2.2. No, I think that's in 2.2.3. We start to do accessors and so on. I guess maybe we had some of those in 2.1 as well. But anyway, the accessor is just some function that, given a data structure, gives you a piece of data out of that data structure. So you sort of build your own insulation against those lower layers, but you can still get bit by them if you start violating the contracts, as we see in 2.2.2. Okay, is there any other, anybody else want to look at any of the other exercises from 2.2.1 particularly?
No.
I mean, there's for each, which is basically just like a map in 2.2.3. That's a pretty straightforward one. And it's basically, so, I mean, you get to sort of this pure functional programming type approach, and all this stuff theoretically doesn't have side effects. So stuff like map, it doesn't actually change the list in place. It goes through the list and gives you a new one back because it's built it up behind the scenes. And so for each is the case where you want to step through every item of the list and do something. That's not building something, it's actually doing something. And so in their example there, this is how you print every item of a list. And the implementation is very straightforward. You basically just step through it exactly the same way, and you apply your function f, or I guess proc if we want to sort of use the language that they're using here. And so if we evaluate this, it churns through every element of this list and calls this lambda on each of them. And it prints out something, it prints out what the item is, and then does a new line. Okay, so I'd say those are sort of the key points of 221. Anything anybody wants to talk about or discuss further? Okay, cool. Excuse me 1 second here. My cat is crying outside the door, so I have to go move him. And I'll be back in just a moment. Okay, we are back. Or I am back, at least. Okay, so how are people doing? How do you feel about how the discussion's going? Is this helpful? Is this good? Is this
Yeah,
what you want
it's
for the
great.
discussion
It's
section?
great.
Yeah,
Absolutely.
this is good.
Okay. Actually, David, if you've done section or exercise 219, I would be interested to see it because that is one that I did not get around to doing. That is the change counting one. And if you're talking, you're muted.
Okay, can you hear me now?
We can indeed, or I can.
Great. 219. Let's take a look at that. Notice that this actually is Paul's problems. I just took a copy of them and then turned them into them.
Ah, excellent.
So what was the question? So consider the counting problem that they gave us in the other one, and they wanted to do rewrite the procedure using. rewrite the CC procedure so that its second argument is a list of the values of coins to use rather than the integer specifying. So, let's see. I defined CC to take a list of values, and I think it was just kind of like a conditional sort of thing that I wrote up, and you can see it's a recursive procedure. So it's pretty much like what we're learning in this thing of creating of using sort of recursive chewing up stuff. And then I just made sure that it did actually work.
Okay, cool.
I don't actually remember 100% what the other one was, what the other one did.
Basically just that, except you had a fixed set of coins. So you basically you had the U.S. coins baked into the procedure. And so
Right.
this is, okay, well, how do we, so I mean, the repeated theme that the book keeps coming back to is how do you get more abstraction in there? And, of course, one of the big promises of object-oriented programming is reusability.
Right.
And, one of the things that you often get from proponents of functional programming is that object-oriented programming can be very bad for reusability because it's hard to get the right kind of generic behavior.
Right.
That makes something actually usable outside of the context in which it was designed. And if you actually do manage to get the generic stuff in there, it adds so much overhead to your implementation that you end up, it ends up being just a very inefficient process all the way around. And I mean, certainly one thing I've seen in the Clojure code I've written is that you do end up with stuff which is easier to genericize. I mean, you can write something, okay, this is something you have to do. Well, you can write a higher order procedure that does it to a procedure that does it to a list or to an item in a list, then you just feed it to map. Or you
Right.
have, or an example here is the tree map operation that we get in section 222, which we're about to start discussing.
Actually, I was gonna, if you guys haven't heard, I'm sure all of you have, but in case you haven't, there's this website called For Clojure that essentially has a bunch of exercises similar to what we're seeing here. And the neat thing about these exercises is that you can follow other people who are working on it, and then when you finish a problem, you can see how they solved it. And so I think it's very interesting because I think, like, for instance, I'm kind of in a let me try to solve all these problems using recursion, and then I see how other people are solving them. And I see, oh, they're getting something so much smaller and beautiful just by using map or filter. You know? Which is cool, but it's just nice to see how all this stuff is kind of built on top of each other.
Yeah, one of the things that people say is that it's one of the best ways to become a better programmer is to read lots of code. But of course, reading code can be quite a painful operation, and lots of code is not very pretty. So
Right.
one nice thing is to read lots of short code.
Right.
So that site is the number 4 Clojure.
For Clojure, and it's I think it's forclojure.org or forclojure.net or something. .com, yeah.
Yeah.
For Clojure. 4 as in the number 4.
Yeah.
I recommend the site.
I've only done a handful of the problems.
Am I following you? I don't think I am. I don't know if I know your
Foreclosure? I actually don't know. It's been a long time since I did any of them, so I don't even know. Actually, I don't even know what I registered under at this point. I'll have to go back and take a look. If I did, it's probably Pata Programming, but I don't think there's much up there. If so, I was mostly just looking at sort of what it was. Another site that's good is Project Euler.
Project Euler. Okay.
ULER. And that's not Clojure specific. And it's a little more ULER. And so that is, it gives you a bunch of sort of mathy problems, stuff that you can't easily solve. If you try to do it the brute force way, you're not going to be able to come up with a good solution. So you have to sort of think it through. So if you click on problems there, you can get an example of
Cool.
things. So it starts off very straightforward, and you can do these in any language, and then what you submit is your answer that your program spits out.
Oh, okay.
And so you don't actually submit code, you aren't filling in code. So you can do these in whatever language you want. And the archives for this are also absolutely fantastic. Just like you said for foreclosure, if you have solved a problem here, then you can see everybody else's code. And they are in every language under the sun.
Yeah, I'm actually really starting to sort of really get into the groove of polyglottism. I don't know if that's a real word, but
Sure.
you know, just pick up as many languages as I can, just for the heck of it.
Yeah, there's lots of useful insights to be gained. I want to go through and do them in J.
That's a two-edged sword, because it's sometimes, if you're learning all of them at once, it's sometimes hard to keep of how you do the same thing in different ones and so forth. Like, I've been reading a lot of Haskell over the last several days, and am finding some aspects of this conversation a teeny-weeny bit disorienting. Only because I'm in a very much of a Haskell mindset.
Right.
Talking about Haskell, there's going to be an edX introduction to function. I think I posted this on the list.
Yeah, you did.
So it's going to be using Haskell. So you can do some.
Yeah,
Haskell.
I've already registered for that, actually.
Yeah.
Okay, so let me find my notes here for 222. I did not have as many notes for 222 as I did for 221, because I really think that sort of what we've been discussing in 221 is the meat of this pair of sections here.
Right.
And section 222 is how do we do some other stuff with these con cells. And so we go through all the traditional infrastructure that's been built up out of Lisp for lists and list operations. And so let's look at how we can build some other sort of recursive data structures. And so these are specifically, a lot of these are around trees. So,
okay. I should point out that I was reading up on, I was listening to the SICP videos that are from, sorry, am I doing that somehow?
No, that was my fault.
The ones that are from the Berkeley ones from, I think, 2008 or 2007.
Oh, okay.
And the teacher, I forget his name, he makes a big distinction between what a tree is and what we are working with in the following exercises aren't technically real trees.
Interesting. So could you sort of tease that out a little bit?
Well, a tree has to have a data point as the root and has to have children that are trees themselves, a list of trees. That's the definition of a true tree. And what they deal with in the problem is really this thing that's sort of like a tree but not quite a real tree, because I think the top level or the children aren't necessarily a list of, they aren't necessarily trees themselves, right? Because they end in data, right? Like 1 is not a tree, 2 is not a tree.
The leaves, you mean? Talking about the leaves?
The leaves, exactly. The leaves are not trees themselves, whereas In a true tree, the leaves would be trees. They would be trees that whose leaves or whose children are empty.
Yeah. Or nil, maybe?
Or yeah, empty, nil,
No.
same thing.
Yeah, yeah.
Interesting.
An empty list, yeah. But I mean, that's not a bad, but it's just I'm just pointing that out because I was like, oh, okay, that's interesting. I didn't, and there are certain
that
things
is interesting. Go ahead.
you can do with a true tree that you cannot do with these things. That you have to sort of take into account the fact that with a true tree you can just map right through it, and it's beautiful because it's a tree, and you know that every point of it is going to be a tree. But with these structures that are tree-like, you have to sort of say, is this a pair or is this not a pair, and then do something, a conditional thing, or whether it is or it isn't, and that's the difference.
Right, okay.
That's cool. So actually, that calls back to sort of one of the footnotes from section 221, and that is about the closure property. So. And the authors are extremely grumpy that the fact that closure now tends to mean something different in functional programming. Specifically, it means a particular way of capturing variables from the larger lexical context and baking them into an anonymous function when it's created, or a lambda, I guess I should say. And closure in the mathematical sense means that whatever you're operating upon is closed under a certain set of operations. So that means that if you apply an operation to something, what you'll get back is something that is effectively of the same type.
Right. Oh, so that's interesting. So that tree, I guess, is a closed object in a way.
So in the sense you're describing it, so the tree is closed, but it seems as if, based on that description, I'll have to go watch that video now, that the underlying representation is not as cleanly implemented, and hence is not necessarily closed under the same type of operation.
I think I should point out that you can actually, using regular old scheme, you can implement true trees. It's just that you have to realize that the lists aren't actually trees. Lists of lists aren't trees. They're just list of lists.
Mm-hmm.
Right.
It's a convenient representation that doesn't take too much code to write in the course of the programming assignment.
Yeah. I mean, and there are things that you can do with a tree that you cannot do with list of lists. So, but they are tree-like. So,
Yes, they are tree-like structures. So, and we do end up implementing a tree-like map in the course of these exercises here. Okay. So, so looking at what we've got in here, it's pretty straightforward. It starts off with a description of using, sort of car and cutter recursively, which is, again, pretty straightforward stuff. It's, how you come up with these horrible strings of car and cutter to recursively walk down to select out the 7 from each of these nested lists. And, that's pretty straightforward stuff as it goes.
Oh, you didn't use like the
Yeah. I guess they were mentioned in a footnote, so I could have technically used them. So in doing these exercises, I have tried to mostly limit myself to the stuff that's been introduced in the text at that point, as opposed to using something shiny that I knew was coming.
I thought the whole point of these exercises was to actually force us to use the CDDDR or CAAR. But
which exercises is this?
The ones where they were asking us essentially to look, get the. Well, maybe I'm wrong about this, but.
So all they say is give the combination of cars and cutters that will pick 7 from each of the following lists, and so that's fine. Now I don't know how deeply they're implemented in a normal Lisp here. Let's.
I think they just go to 4, or I could be wrong, but.
So, so let's see. Do we have our L1 here? No, we don't.
What exercise number is that, by the way?
25.
25, okay. Yeah, I just add a bunch of kadars to this one. But I think they've introduced these already. They introduced these, I think, like in the last section.
They introduced them in 221 in a footnote. So yes, it is perfectly legitimate to use them, but I didn't actually have them a notation to discuss that during the course of this one here. So
Yeah, I just assumed that that's what they wanted. They just kind of wanted you to practice that.
Yeah, and of course it can be kind of messy to. There we go. Let me get L1. We won't worry about that. That's pretty straightforward. So. Okay. And and I just did there was my cheat for doing the last one. For chugging through, and I did use compose here, which is a higher order function. So this one is technically part of the exercise. So all compose does is it takes two functions and sticks them together. So it applies one and then applies the other, just like functional composition in mathematics. So you get a new function that does both.
I just did kadar 3 times.
Perfect. Yeah, exactly.
Kadar.
Yeah, but again, the main point of that is once again to just get you thinking in terms of what's going on with these lower level data structures. I mean, if you're writing Clojure, you'll never see your car or cutter. You'll be using first and rest.
Right.
But for the rough semantics are completely analogous. And what this does also tell you is that you don't want to be doing these low-level operations manually. You want to start writing your own accessors that are aware of the way your data is stored, but you don't make mistakes when you start fetching it out again.
Right.
Anything here? No, that's just this is what lists are. So if we append something, two lists together, we get. Well, that's the first one here. If we append two lists together, we just get a new list that has all the elements together.
Right.
And cons one list to another list. What we end up with is the first list in the first position as a nested sub list, and then everything else is the tail. And then if we do a list of each of these, then we get two separate sub-lists. We get a list that has two elements, and then each of the lists is a sub-element of that list. So again, this one's really just about understanding the tools you've got at your disposal. There was one here that I found a pain to do. Was it this one? Okay, this was not the one I found to be a pain. This is the deep reverse procedure. And so this is, you want to reverse not only a list, but you want to reverse the sublists as well.
Yeah, like flattening it out, basically.
Except you leave them in place, just that each sublist ends up in reversed order.
Yeah.
Where I've got a lurking. So we don't have L1, but we have a Z. Okay, we've got a Z here. So here's an example of Z. If we reverse Z, you can see it just does a single level swap of these guys here.
Okay,
and
right.
If we use the deep reverse Z, the lists are going to remain in the same. So it swaps the list, but it also swaps each of the lower level lists as well. So it's basically going down recursively.
Right, right.
And if we nest another level in there, gives us that, and ZZ, and deep reverse ZZ. Keeps going down to, you know, the third level list down there.
So, Paul, can you display your implementation of that? Oh, there you go. Thank you.
Sure.
Yeah, my implementation was different because I couldn't figure out how to do this using cons. So
okay, shall
I
we take
ended
a
up
look at your
using
implementation?
append.
Okay, let's take a look at your implementation. Yeah, comparison's great.
Sure. I just could not figure out how to do deep reverse using cons. I ended up using append as my, and I tried so hard to do this with cons.
Okay, maybe this was one. There were at least two of these. One of them took me an entire train ride to do. I think it may have been tree map, but this one was a little tricky as well because it doesn't work out quite the way you expect. Okay, so so describe your implementation for us.
Oh, sorry. So my implementation essentially takes the list and then is a null list and just return the list, and append deep reverse of CDR of list, right, the first part of list, to, and then it just branches off. It says if list is the pair, then append that the list deep reverse, because that returns a list, or return the car of list. So it kind of just like does that, but I could not figure out how to do this with cons. Like appending just kind of made sense to me.
Right. Well, and in fact, appending is a perfectly legitimate way to implement this. But do you want to take a look at the cons one a little more closely here?
Yeah, actually, can you put that up again?
I can.
Can you like walk me through it in terms of like?
Okay, I have to recover my own thought process here. Am I sharing my screen successfully? You see this?
And now, when you do this, does this actually work? Did you test this?
I did. In fact, we just saw it working right here.
Right.
Okay.
So that is the result of that exact procedure there. Okay, so what we do is we first start off defining this little helper procedure here. Okay, so what we're doing is we're defining, so we've given a list, we're going to say, okay, the first thing we need is this helper procedure. What the helper procedure takes is a list and then what we're going to be returning. So if this is the same kind of thing that we see in building a lot of the iterative recursion.
Right.
So what we have here is we recurse at the start we're going to kick off our helper procedure here with the list and then nothing as what we're going to return. Okay. And so then if our first thing is a null, then we're going to just say, okay, that means we're at the bottom for this step. So we are just going to return whatever we have built up already. So that means everything has been moved from list to rent, and then return that. Otherwise, if it's a pair, we're going to do, okay, on the cutter, but we're going to stick that on the left side, and then on the right side, then
okay.
This here is going to be the rest of what we're returning. So this is stuff that's going to be finished when we're done with it here. This is all getting moved into the ret of the return of the recursive call.
So this is a bit more complicated because you have two recursive calls sort of intertwined in this.
Yes, and in fact, that was what gave me a bit of a headache here, because got, first of all, your helper, and then you've got this call to the outer one where we're actually starting a new reverse.
Yeah, that's impressive.
Paul, the recurse that's down, the recurse that precedes the, I guess it's on the third from the from the last line.
This one or this one?
Well, I don't know. I'm not seeing it on the screen anymore. I'm seeing. Oh no, there we go. Yeah, that one. The one where the R is highlighted. That is actually placing its results into return, right?
So what it's doing is it's making a recursive call here. So this is what's going into return. Okay.
Okay. So how does the CDR list is the first. I see. It's the first argument to recurse.
Exactly.
And I got it. Okay. I see it.
You know, and like, you know, Paul, like I sort of intuitively sort of understood that it would have to be something like this, because I was like, well, you know, because what was happening with when I was trying to do it was that it would just end, right? And I needed a way, right? Because you would give it the last one, and it would just like collapse, and then you'd have nothing. And then I tried some other things, and I get a reversed order list, not what I wanted, like a left fold or whatever. And but yeah, this I could not figure out how to do it. This is pretty impressive that you managed to use.
I'm pretty sure this one. Now that I'm looking at this, I'd forgotten about the double recursion, but I'm sure that gave me quite a bit of trouble. Because I was getting, I wish now that I'd sort of kept my interim solutions that were turning up bad stuff. Yeah, because if you just make this a regular recurse, it won't work.
Right.
If you wanted, you could sort of cheat, and you could actually not do a deep reverse. You could just make this a regular recurse and start with a new null here for ret, which is effectively the same thing. So we could actually change this here to recurse carlist ret and null, like that. That's effectively the same thing. And so that's sort of a little tidier from, you know, sort of the definitional perspective. But it doesn't really make much difference since, you know, it's not creating like a new one of these every time it gets called.
Okay. Pretty cool.
Okay.
Actually, can you make that? Can you like make that work? Can you actually turn it? I just want to see if.
You want me to?
Not this one, but when you just keep it as the not the double recursion, but just the single recursion.
Yeah, let's give it a try here. Absolutely. Oh, believe me, huh? Okay. Okay, and this will be a null. Okay.
You're recusing yourself.
Yeah. Okay. Ooh, that was it. That was it. That's why it won't work.
Exactly. Yeah.
That was it. Okay. Oh, recuse. Oh, okay.
I was just saying.
Spell reverse. Okay. There. Okay.
Oh no, yeah. There you go.
Okay.
You must have a vested interest in the solution.
Well, did that work?
That worked.
Yeah. No. 432 is. Yeah. That worked.
It's exactly the same as the other one there.
Perfect. That's amazing.
So. Okay, so I'm just going to switch, actually, reverse, and I'm just going to make another copy of that for my notes here, because that will be interesting for a write-up. Okay. Actually, I did hit another one. I think that was probably in 224, where I ran into exactly that kind of problem, where if I was just defining something using lambdas, but I couldn't recurse. It couldn't recurse to itself because it hadn't been defined yet, or something like that. But yes, but this name is actually defined inside of the define, so you can actually use that as a recursive call. Okay. Okay, are there any of these other ones that are worth discussing? This is pretty straightforward. Fringe is just saying, okay, we've got a tree. How do we get the quote leaves off of the tree? We know they aren't. This isn't really a proper tree based on a.
This is another one that I used append. You probably use cons, right?
Nope, I used append for this one.
Oh, okay.
I used append for one version and cons for the other. So it's the right semantics for the task at hand. So actually, I hadn't even thought of using append for the other one. Maybe I should have. Might have ended up being a little tidier. So I don't know that we need to. Do people want to walk through the code of this one?
No, I think it's getting kind of late. So
yeah, that's what I'm thinking too. So let's see. I didn't do 229. I didn't do 224 because I got bogged down with trying to come up with a nice thing to do graphical box and pointer representations. And so I guess maybe just we'll take a fast look at 231 and 232 here. 230 is sort of the lead up to 231, where we define a tree map.
They remember who was there.
230, okay.
Boys weren't together. They like totally like.
And again, this is a pretty straightforward one. I guess we probably don't need to walk through the code of this specifically, but you can see it's pretty straightforward. We've got our little helper function inside a tree map. It recurses down, and wacky.
I did this different than you did.
It wasn't both all that hungry.
Interesting. I wonder if I have that a little off there or something. The results are correct. Okay, I'm going to have to go back and take a look at this one.
What did I do? I think I used map. Just was I not supposed to do that? I think I cheated.
Okay, let's see here. Let's take a look at what you did here. I think that's probably legitimate. So let's take a look at yours, David. Go ahead.
Yeah. So this is the one for problem 230, 2.3, 2.30.
2.30 or 2.31?
Oh, 2.31. Is that what we're looking at? 2.31.
We were looking at 230. 230 leads into 231, so 231 is sort of the generalization of 230. So let's look at 230. That's fine.
Okay. So I mean, it's pretty much the same solution for both of them, but I say define a square tree, then I map subtree if pair subtrees. I guess, does this even work? I guess it does.
Yeah, I was having the same problem looking at my code. It's like, it's getting the right result, but that's what I'm looking at. I can't remember why. Yeah, actually, you've got a nice, tidy solution there.
Yeah, my solution seems to be, because what are you? Let me look at yours real quick. Okay. It says that you're doing this thing where you're like defining a helper function inside.
Mm-hmm. Yeah, I think for some reason I was attempting to avoid using map, and I think that we needn't fear map for the purposes of this exercise.
I think that's probably like I also tried to. I think I hit my head trying to do this not using map, and I couldn't do it, and so then I just used map.
Actually, I had major problems getting this one to work correctly. This one I was just banging my head against it, and
I guess there's a reason why they build map.
Yes, exactly. Yeah, but you know, it is useful, I think, to just sort of spend the time bashing your head against this stuff and seeing what doesn't work and why, because you have to do that bashing your head at some point during the learning process, and it's better you do it now than before you're writing production code.
Right.
Of course,
I mean,
anyway.
I bashed my head, but then I failed. I mean, you actually managed to make it work.
Yeah, the problem, though, is it looks like there's some kind of almost magic going on in there. I really should have put some comments in that, because you see I've got up here my little comment, write up, which is my notation that, okay, I've solved the problem, now I need to say why it works.
Right.
And I think I'm probably going to have to step through that one to see, okay, so what's going on here? So we've got tree map, which applies function to a tree, which is tr here. Okay, we've got a helper function, and all the helper function does is it takes a tree. What is the point of that?
Well,
Okay, because it is... okay, that's what it is. Okay, so this gives us a single function. So what this does, tree map here closes over f. Okay? So f does not have to be supplied as a parameter, the tree map h. You see? Because it captures it from the outer scope here. Okay? So tree map h just takes a single function, and that function is a tree. Which means, we can actually use it. So I did it with a map here as well. But so all this is doing is this is defining something that is a single argument function that can be applied to a tree.
okay.
And so that gives us three tidy cases here. A null, in which case it's null. If it isn't a pair, it's the value of the function applied to tr, which is, the thing that's not a pair. It is the leaf. And the remaining case is it is a pair, in which case we map over it using this single argument helper function.
Right, and I'm gonna go and start ironing my clothes.
And so I could have done that with a lambda there as well.
Yeah.
And that might have been a little clearer, actually, because it's a little weird seeing it sort of just sitting there on its own like that when you're used to having the helper function sort of wrapping around everything that follows. But really, the point of that tree map h function is just to give us a one-argument function that can be given using map.
Oh, and then just want to point out something for this 2.30 and 2.31, at least in the way I solved it, which is that this is indeed a recursive solution to the problem, but we're kind of hiding the fact that we're returning a null, we're returning a terminating value by using map. At least, which I think is pretty cool that you can do that. But,
Right. And then I suppose that if we were to take that a level higher, once we have tree map working, we can stick anything we want to at the nodes of the trees, and then use tree map itself as a similar sort of primitive.
Right.
Okay, so that's kind of a fun one. Okay, I better write that one up, like with the actual solution before I have to go and figure it out again. And I'm pretty sure that this one gave me fits as well. Okay, so they don't describe these as power sets, but that's what they are. So the power set of a set is the set of all subsets of the set. And so the goal is, given a set, which is just a list, we want to come up with all the subsets of it. And so that includes the empty set, each of the single elements, two-element sets, and then the set of all three elements. As this.
Oh my God! Yeah, this one was really difficult.
Yeah, this one also gave me serious fits.
Wow.
Because I came up with solutions, but I also was trying to figure out why my solutions did not come out in the same order as theirs.
Oh yeah, exactly. Yeah, I was
They
hitting that.
clearly had something in mind, and I was trying to figure out what it was.
I think I ended up cheating. I think I looked at someone's answer.
Oh, okay. Yeah, there's a couple of solutions out there. Sometimes I will look at the answers, but I try really hard not to do it until I've actually solved it myself, or at least come up with the critical bit myself.
I'm not 100% if I cheated, but I wouldn't be surprised.
Okay, let's take a look at yours, David.
I don't. I mean, this is ugly.
Yeah, that's okay. Ugly's fine.
Let's see. Subsets. Why am I defining subsets twice?
Well, you define subset. Well, probably one. Maybe one is your own one, and the other one's the one that you.
Just probably, yeah. I think mine is the one that the one is the one up here. I don't know. For some reason, I define it twice. I think mine is the ugly one, and this one up here. Yeah, I think that's what it is. I figured it out, right? This is mine, the one on the bottom, the ugly one, and then I found this one up here, which is much better.
Ah, okay.
The one on the top works.
Okay, did yours end up working or not, or did you?
Yeah, mine works. It's just horrible looking. So don't look at it. Just
okay. Okay, so let's look at your solution that you've got up there. If that's the tidy one for
the tidy one, I think.
Scroll down a little bit. I've got a Google Plus over. Okay, thank you.
Yeah.
Okay, what do we have here? We've got. Okay, we start off with subset of item.
You know, it looks exactly the same as like the other ones. I wonder why.
Rest. Subsets. Okay, that is a pretty tidy recursive definition. Okay, actually, I wonder if I ended up using append in mine. Let's take a quick look at mine here for comparison. Yeah, mine looks pretty similar to that. It uses append.
Yeah.
Append and map. Okay, but I ended up so I could have I didn't, and in this case I ended up not pulling the lambda out as a helper function. But basically that other. Go ahead.
I'm just wondering why did I think I needed to use a filter function? Like why?
Well, I can see why you might reach for that, because if you've got, I mean, if you're thinking of it in terms of a set, so you've got, you know, your set of this item and then the rest of the set with that item removed, and maybe you were missing out some items for some of the set combinations.
Huh. Anyway, clearly, my solution worked, but it's horrible looking.
Okay, so I think that is sort of all of the exercises. I think that's all of the discussion. Any sort of thoughts, questions, comments before we sort of close it off here for tonight? Because I know we've been going.
Oh, this really makes me want to go and do the problems now.
Ah, awesome! That's a great result.
Ditto here.
The problems they're really what teaches you. I feel like when I read any of this stuff, it kind of sort of makes sense, and then I realize I don't understand anything once I start doing the problems.
Well, I went to this thing in New York the other day for F#, and and part of the presentation involved a hands-on exercise that everybody around the room did. And what I did was I headed for the advanced track rather than the beginner's track, because I figured it would cover things that I wouldn't be able to, learn off the web or, whatever. But boy, was I ever humbled, because everybody in the room is sitting around, just racing through these exercises.
Yeah, I think a lot of these exercises, though, they seem to be kind of repetitive, and lately I've been going to this thing called SC something Philly. It's not SICP, but it's like code, software as craft or something, or coding as craft.
Oh yeah, I saw an announcement for that. A couple of my guys from my workplace go there.
Yeah, well, the interesting thing about this is that at the end of each one, so they have like this sort of, the beginning of it is sort of discussion, it's sort of very sort of cerebral, sort of talking about what is coding and whatnot and stuff like that. But at the end of it, they have these koans. It's not quite koans, but problems that you're supposed to partner up with someone else in the room, and you can solve it however you want. And then at the end, everybody discusses their solution and blah blah, and stuff like this. So it's really interesting in terms of like practicing. But what I've noticed with the last two that I've gone to is that the problems that you can give are it's going to be a certain type, and then it's almost always the same. So I think if you get practice with that, I think you're going to be pretty good at it. You know what I mean?
Mm-hmm.
But the other thing is this book is definitely changing the way I think about problems. Because the first thing I want to do to everything now is turn into a list. Turn into a list and then figure out how to add map to it or filter it or do something like that. And that's which was not what I used to do before.
Yeah, that is good, because I do find I found that, you know, sort of after I was first learning functional programming, I found I was really missing a lot of these tools in other languages. So I was doing Python at the time, so I was trying to figure out how to make my Python as you know, as functional as I could.
Yeah. Well, you know, it turns out that Ruby is actually pretty functional, and I'm sure Python these days must be pretty functional as well. They're all borrowing stuff from each other anyway.
Absolutely.
I think they all have Lambda functions now. That could be like even PHP has a Lambda function.
Oh, do they really? Okay.
Yeah. Yeah, PHP wasn't going to be left behind.
Reassuring as it might.
Actually, want to know something? This is the interesting thing. I'll stop at that. But so this Haskell class that's going to be it's going to be on edX. So it's going to be on. They're going to teach functional programming using Haskell, but the very end of it, they're going to apply it to PHP, to hack. What you learn, everything that you learn, to hack, which is a version of PHP. So
awesome. Okay, that sounds pretty cool.
and I added a link. I don't know if you noticed in the very beginning, I added a link that was cons, car, and list implemented in JavaScript, just so that you guys know that you can actually do this stuff with JavaScript.
Okay, cool. You should post that out to the against the meeting as well.
Okay.
So it persists after the chat ends here.
All right. Well, it was great, guys. I enjoyed it.
Awesome. Well, thanks a lot for showing up, everyone.
Thank you for hosting this. Wow.
So,
Thanks, Paul.
Thanks, Paul.
I think the next one will be on October 27th, and there'll be shortly thereafter there will be the in-person one for Section 2.3. So
all right.
keep chugging.
Okay.
Great.
Okay. Thanks, everyone.
Great.
Bye.
Bye.
Good night.
Yeah.